Hi everybody, welcome to the next lecture on Multimediale Werkzeuge. Today will be about sound and audio objects. So here are a few formats and examples. Well known is, for instance, MP3, which is short for MPEG 1, 2, layer 3. Then PCM, which is for pulse code modulation. This is pure raw samples. Let's say raw samples. Not data, but samples. And common formats here are, for instance, on the CD, we have 44,100 Hz sampling rate and 16 bits per sample. So that means we get 44,100 samples per second, and that also gives us the limit on the maximum frequency we can represent with it. So here's an example which shows where we go to the limit. This is actually a limit case. So imagine we have a sine wave with 22,050 Hertz. So we have 22,050 periods per second. So now imagine our 44,100 samples, so twice as much, just appearing at the zero crossings of this sinusoid. So we can see here we have one period and we get two samples for each period. But these samples happen to fall on the zero crossings, and that means after sampling we will have only zeros, right? So that's an example where it doesn't work, right? So that means our audio frequency should be clearly below 22,050 Hertz, right? We need to have some distance below. Yeah, and 22,050 Hertz is also called our Nyquist frequency, and all our audio signals should have frequencies which are well below this Nyquist frequency. So in practice, frequency content needs to be less than about 20 to 21 kilohertz. Also because the transition bandwidth from pass band to stop band of the low pass filter before sampling to avoid aliasing, and in the A to D conversion, and after D to A conversion, there's another low pass filter. Both are not ideal filters. So they have a transition band which allows the filter to go from passing to stopping. So the filter needs some spectral space to go from passing in the passband to stopping, and that's why we need to be clearly less than Nyquist for our audio frequencies. Right, so yeah, and this is basically a consequence of the Nyquist sampling theorem, which says that we need to low pass filter before sampling or downsampling to avoid aliasing and to be able to recreate the low pass filter version after reconstruction, after upsampling or D to A conversion. Yeah, so audio signals are usually represented or quantized with 16 bits per sample. And this leads to quantization errors or quantization noise, right? If it's audible, then it sounds like noise. So what is their signal to noise ratio then? So here we consider the power, so the power of the signal divided by the power of the noise, right? So from quantization we get an error, and this error has a power. So there's actually a rule of thumb. The signal to noise ratio for the quantization is more or less 60 dB per bit, right? So each additional bit in our quantizer gives us 6 dB more signal to noise ratio. So that means for 16 bits per sample, we have an SNR of 16 times 6 dB, which is 96 dB signal to noise ratio. Right, so that is actually a pretty good value, 96 dB. And this was also one of the original reasons to go from analog to digital, from say tape to CDs, or from LPs to CDs, because in this way you get much better signal to noise ratio. Yeah, but this is actually only true if you have a full signal. If the signal uses all those 16 bits. If the signal uses fewer bits, if it's a weak signal for instance, then the signal to noise ratio is reduced accordingly. Yeah, so now to the dB numbers. So how are they connected? How are the dB numbers for power ratios and voltage ratios connected? So we can simply take a look at the formula. So for power, we take the ratio power A divided by power B. So power A might be the signal, power B might be the noise. Then we apply the log base 10 and multiply by 10. So that's also where the name decibel comes from. The deci comes from this 10 in front of here. And power in turn can be computed from the voltage. Right? We square the voltage and divide by a resistor on which this voltage is applied. Right? So voltage A squared divided by R divided by voltage B squared divided by R. And we can see the R cancels. What's left is A square and B square, and the log of a square allows us to rewrite it as a factor of 2 in front of the log. So the square inside the argument goes as factor 2 in front of the log, and then the 10 turns into this 20 here. Right? And this is the expression for dB if we have voltage ratios. So if the argument here is voltage ratios, or it could also be current ratios, then we need to multiply it with this factor of 20 and we get the same dB number. So this makes the dB number independent of if it is a power ratio or a voltage ratio. Yeah, and I just applied this rule here. Yeah, that's convenient, because regardless of the choice of power or voltage, for our ratio we obtain the same dB number. Yeah. So back to our example, 96 dB in a voltage ratio. We want to know what voltage ratio do we get. Right? We know that we have 96 dB signal to noise ratio using the 16-bit A to D converter. And then we want to know what voltage ratio does this correspond to. So we know 96 is our SNR in dB, and that's 20 times log base 10 of signal voltage divided by noise voltage. Maybe I should rewrite this a little bit. It looks a little bit strange here. So we have the SNR in dB is 96. So now we just need to solve this equation for this ratio, signal voltage divided by noise voltage. And we do that by dividing first by 20. Both sides are divided by 20, so we have 96 divided by 20. And to get rid of the log base 10, we take 10 to the power of this expression. So then we have 10 to the 96 divided by 20, and that's our signal voltage to noise voltage. So maybe it should be consistent here. Signal voltage divided by noise voltage. Okay. Yeah, and putting this, for instance, into Python and compute it, we get 63,000, right? So that's the ratio between the signal voltage to the quantization error voltage. So it's quite a large number. Yeah, and an important property of the dB measure is that multiplication of factors become additions of the dB values, because it has a logarithm. And that's also convenient in practice. So for instance, imagine we have two attenuators or antenna cables with an attenuation factor for the power of 0.1 each. So here we need to specify this factor is for power, not for voltage, unlike dB. This corresponds to a dB value then of 10 times log base 10 of 0.1, and that's minus 10 dB. Right? Because this is smaller than 1, we get a negative number. Over the two attenuators, we get a total attenuation of that product, hence 0.1 times 0.1 equals 0.01. This then corresponds to minus 20 dB. We can now avoid this multiplication simply by getting the corresponding result by adding the two dB numbers. We have minus 10 dB plus minus 10 dB equals minus 20 dB. Right? We can see it's the same. This is useful, for instance, in a studio for fast in-the-head calculation of a total attenuation of a connection with multiple cables. Right? So convenience. Yeah, and that also helps to have a few numbers in your head. So memorize those numbers because that makes things easier for the calculations. So 0 dB is easy because if a log of something is 0, then the argument must be 1. Right? So the voltage ratio is 1. So the signal voltage would be equal to the noise voltage, for instance. Then we have 0 dB. The log of 1 is 0. Right? 10 to the 0 is 1. Then, not quite as obvious, 6 dB for voltage corresponds approximately a factor of 2. Right? And a factor of 2 is also easy to remember. You just have to remember that factor of 2 for voltage means 6 dB in the dB scale. Then we have factor of 10 in voltage is 20 dB. Half of 20 dB, so this is what we just saw, right? Half of 20 dB is 10 dB, and a factor of 1/2 in the dB scale must be an exponent of 1/2 in the original ratio domain. So power of 1/2 is the square root. So we get a square root of 10 here for 10 dB in the voltage domain. Then 1000, so we have 3 zeros, is 10 to the third power. So we have the exponent 3 multiplied by 20, we get 60. Right? Then the negative numbers are just 1 over the positive numbers. So minus 10 dB here is 1 over square root of 10. Minus 20 dB is 1 over 10. Minus 60 dB is 1 over 1000. And that means minus infinity goes to 0. Right? And that's also something to remember. Log of 0 goes to minus infinity. Right? So this is also very important when you program something. For instance, when you program the plot of dB numbers, then it can easily happen that you have a 0, for instance, in the transfer function of a filter. And then you need to capture this case either by some if statement, but it's actually easier to just add a very small number, a small epsilon, to avoid errors in the computation. Yeah, and this comes because the log of 0 goes to minus infinity, which is not a number. Yeah, then those simple rules, which I just already used. So if we add two dB numbers, that corresponds to the dB number of the product. If you multiply a dB number, then this corresponds to the dB number of the number to the power of this factor. Alright, so back to the formats. What sampling rates are common? So Quite common is 32 kilohertz. That's also because the Nyquist frequency is 16 kilohertz, and that's just at a normal upper limit of hearing. Then we have also 22,050 hertz. We have 11 kilohertz, something that Apple introduced. We have 8 kilohertz, which is used for speech, because for 8 kilohertz the Nyquist frequency is 4 kilohertz, and there the audio bandwidth up to about 3.5 kilohertz is used. Remember, we need to have this transition band from passing to stopping. So here this transition band goes from 3.5 to 4 kilohertz. So everything between 0 and 3.5 kilohertz is then usable audio, and for speech that is sufficient for telephone quality. So it's not great, but it's understandable. Yeah, on the other extreme we have 48 kilohertz for higher quality audio, then 96 kilohertz, which is used in studios, for instance, or even 192 kilohertz high quality audio. So this is useful not for the high frequencies, but for processing. If you have some nonlinear processing going on, then you will get possibly alias components, and their position and frequency is determined by the sampling rate. So if you have a very high sampling rate, that means your alias components are also very high and can easily be removed. Yeah, and for the quantization, or the number of bits per sample, we already mentioned we have the 16-bit, which is quite common. So common for audio, 16-bit per sample. But we also have 8-bit. For speech, and for audio we also have 20-bit, 24-bit and 32-bit for higher quality. Right, so let's take a closer look at quantization. So for audio, what's mostly used is uniform quantization. It uses the subdivision of the possible amplitudes into equal quantization intervals. Right, so imagine we have n bits, capital N bits, for instance our 16 bits. Then the quantized value of x is x divided by delta, the quantization step size, and the rounded. That's our quantization index then. So this quant of x is also called the quantization index. Then this delta, the quantization step size, simply is computed by taking the maximum possible value minus the minimum possible value and divided by 2 to the nth power. This is the number of levels we get with n bits. Right, so it makes sense. So we basically divide this this range of values into the corresponding number of values we can represent with n bits, so 2 to the n intervals. So maybe I can add that here, called quantization index. It doesn't quite fit in here, so that's better. Right. So this is what you would do on the encoding side. And on the decoding side, the reconstruction, we need the reversal of the quantization. So quant of x indicates the quantization interval, the number of the quantization interval, which is the quantization index, right? So here I already mentioned that. Hence the reversal for the reconstruction is simply taking this index, this quantization index, and multiply it with the step size, right? Then we are getting back into the original value range. So it's actually quite easy. So here's an example. X shall be in the range between -1 to +1. And we have a value of x equals 0.6. And just 4 bits for the sake of this example. That means we have a delta, this quantization step size, of max minus min, which is 2, divided by 2 to the 4th, which is 16. So that's this value. So total 1/8. And that means we can now quantize x by taking this value, 0.6, divided by the step size, 1/8, and round it. And we get a 5. So 5 is now our quantization index. So here 5 is our quantization index. Yeah, and here also note that the quantization index, quant of x, could possibly have a sign if it's a negative value, right? There are different approaches to this. One is the shift of the value interval so that only positive numbers appear, right? We can shift it before quantization and shift it back after dequantization. Another is the separate, maybe I can add that here, and shift it back after dequantization. Another is the separate coding of the sign, so that means we have a sign bit, or to use a binary representation which contains negative numbers, for instance the two's complements or the ones complement. So there are different ways. So now the reconstructed value. So here the reconstructed value of this example is simply the index times the quantization step size, 1/8, and that results into 0.625. So we see this is a deviation from the original value of 0.6, and that deviation is the so-called quantization error, which in this case is 0.025. Right. So this is where we can see it again. We have a quantization error. So now let's take a look how it's used in speech. So actually speech was probably the first audio signal which was processed digitally. And at that point, quality was not important, but intelligibility, because it was supposed to help with telephony or maybe wireless communications, narrowband wireless communications. So here they wanted to have cheap, simple hardware and also very few bits. So that's why they came up with the so-called Mueller quantizer. This is a non-uniform quantizer to improve the signal-to-noise ratio for small signal parts. Right? So especially speech, plosives, for instance, are very high in amplitude, and then you have parts of the signal which are very soft, like S and those lower parts, and you have a very different, you have very fast changing amplitudes. And this uses smaller quantization steps for smaller amplitudes and larger steps at larger amplitudes. Right? So it basically adapts to the amplitude, which makes sense, right? So the resulting signal-to-noise ratio no longer decreases significantly for small amplitudes in this way. For speech, Mueller is often used with 8 kHz sampling rate and only 8 bits per sample. So here really it's important because you only have very few steps. And that's why it's so important to make those steps smaller when you have small amplitudes anyway. And if you on the other end, make the steps a little bit larger, then it doesn't really matter that much because the signal is larger too. So here the non-uniform mu-log quantization is important because otherwise there would be a very low signal-to-noise ratio at soft speech parts and clearly audible noise. And that's used, for instance, in ISDN telephones. So here you can see the principle. You have input values, here in this example between -4 and 4, and in the middle is the 0, right? And here is the output. And this is the output after dequantization. So you can imagine we have those numbers going in, then they are non-uniformly quantized, you get indices, and those indices are then turned back into values, and these are the values that you get. And you can see from the rounding, you get those steps, right? But you can see around 0, those steps are tiny, right? But then when you go to larger values, negative and positive, those steps become much larger. Right, but this is where you can afford it because you have a large signal anyway. Here in the middle it's important to have small steps because otherwise the signal would disappear here. Yeah, right, so this is what we just saw. Output of the dequantizer. Yeah, and the implementation is actually using a uniform quantizer, but before and after you use functions, nonlinear functions. So first you use a compression function before uniform quantization, and then after dequantization you use a expansion function. So before uniform quantization we use a nonlinear function for compressing the value range, and after the uniform reconstruction we use the inverse function for expanding the value range. So for Mueller, for instance, we have a 16-bit A to D converter, so that we are already in the digital domain before we apply this function, because it's easier to apply this function on a computer instead of using analog electronics. I mean, it's possible, but then we get additional errors because analog conversions are much less precise. Yeah, so let's assume we have this 16-bit A to D converter, and then we normalize it into a value range between -1 and 1. So basically taking those 16-bit integers and turn them into floats in this range. And to floats we can easily apply a log function, which we see here next. So here's our nonlinear function. This is our mu-log compression function. And you can see here, indeed, we have a separate sign bit. So this is actually, the sign is kept separate, or sign function. I mean, I don't say this will be a separate bit, but it could be, but it doesn't have to. Yeah, and then inside this log, we just have the magnitude of x, which is also important because the log cannot take negative numbers. Right, so here we have log of 1 plus mu times magnitude of x, and here we have a constant in the denominator, log of 1 plus mu. Right, so this is the fixed number, so we actually don't need to compute it every time, we just pre-compute it and then store it. Yeah, so this is actually the only function that we need to compute, plus the sign here. So these values are then sent to an 8-bit quantizer. After the 8-bit dequantizer, we apply the inverse function for the reconstruction. So here you can see this is the inverse. You can just solve this function here for x. So here we get sine of x, sine of y in this case, then 1 over mu times 1 plus mu to the power of y minus 1. So after some computation, you can then get the x out of this. So this is the x dequantized. Yeah. Okay. Strictly speaking, this is dequantization of y. And this is then, let's call this x reconstructed. Maybe that's easier. Yeah, so in principle, we just need to apply those compression and expanding function, and this is also why this is called companding. Yeah, and the resulting bitrate can be computed like this. We have 8,000 samples per second, then we have 8-bit for each sample, and together it gives us 64,000 bits per second. Right? It's not very low, but it's not very high either. As a comparison, the bit rate of a CD, right? We have 16-bit per sample, 44,100 samples per second, and that gives us a bit rate of 16 bits per sample times 44,100 samples per second is 705.6 kilobit per second. So when you compare this, it's a factor of 10, more than a factor of 10 in between, right? Here we have 64 kilobits, so the 1,000 is a kilo. So 64 kilobits, and here we have 705 kilobits. CDs are actually stereo, so it's twice that much. Yeah, then we can also compare it to the compression rate of MP3. For MP3, for a mono channel, we typically have around 64 kilobits per second. So interestingly, it's pretty much the same as the bit rate for MuLaw PCM over ISDN. So here's 64 kilobits, and here we also get 64 kilobits. And this is also because originally MP3 was targeted to enable music transmission over ISDN lines at 64 kilobits per second. So this was actually one of the driving applications for the development of MP3. Yeah, and that means for MP3 we get a compression ratio from one mono channel on the CD, which is 705 kilobits per second, to this 64 kilobits per second, which is a factor of 11. Right, and that's significant. So we obtain significant compression with MP3, which means it's not just a format for representing audio, but it's also a powerful compression. Yeah. Then we come to more audio formats and tools like Adobe Audition and Audacity. So first, let's take a look at the PCM signal as it comes from the microphone, for instance. So here we have, again, our signal. Here we have our samples, and our samples are quantized, for instance, using 16-bit. Here we have our sampling interval, the time distance between one sampling to the next sample. Yeah, so we have those 44,100 samples per second. Each has 16 bits, and that means we have 2 bytes. And in computers, there are actually 2 ways to order those 2 bytes per sample. Right? 1 byte is 1 byte, it's the same, but 16-bit, you have 2 bytes, so there are actually 2 different ways to order them. Yeah, so there are various computer architectures that internally represent 16 bits with first the higher bytes or first the lower bytes. Accordingly, there are 2 representations for PCM audio formats, depending from which architecture they come. One is called Little Endian, which means the first byte is the least significant. Then the other one is Big Endian, which means the first byte is the most significant. Yeah, so unfortunately this is not standardized, so you have those differences. So this is information that the user must know if that audio signal is present in the so-called raw audio format, which means the file contains only the samples of the signal and no additional information. So this information needs to be somewhere else, which is unpractical. So for this additional information, the so-called headers are used in audio formats. For instance, in these formats. So if you have .au, .smd from Sun, .aif from Apple, .wav, these all contain headers, and those headers, they contain this information, among others. So the information that these headers include is if it's little endian or big endian, the sampling rate, the bits per sample, if it's linear or mu-law characteristic, or the use of compressions such as ADPCM, to which we come in a moment, or simple comments on the content. Right, so here I call both capital, so I should also have this capital here. Okay. Yeah, and here's an example how to include audio files in web pages in HTML. So we can set a link to the audio file. So this is pre-HTML5. Basically here you need to have just a link to the audio file, and then you leave it to the browser how to play it back. So here's a very simple example. Here's our web page starting with HTML. Here's the head, the title that appears on top of the browser window. And here's now the body. Here the header, sound file. Here paragraph. And here we have now the sound file, the link to the sound file. So here we see we have href. This is the link that I set now. Here's the text to it, and here is the file name, and then here more text is sound file. And we can now try it, just open it in Firefox from a terminal shell, for instance. Copy, and then let's see if I have a window here. Yeah. So here's my Ubuntu window, and let me now paste this command using ampersand to keep my terminal usable, and now start Firefox. No? Oh, interesting. Ah, here you go. Okay. So here you can see it points to my soundlink.html, and this is exactly what we expect. So here the header, then here the link with the text which points to the file of the same name, and then some additional text. So let's see if it works. Yeah, so here it opens its own browser. So this behavior depends on what browser you have. You might usually have a built-in player in your browser. Okay. So here's then an example with HTML5. So HTML5 has audio objects defined in its standard, right? So that also means that any browser which can handle HTML5 also has this capability of audio playback internally, right? And this is basically what we just already saw. This browser, Firefox, could play back audio. But using HTML5, you have actually many more possibilities to control the playback. So here you can see it's basically looking the same in the beginning. But here now we have audio source. So the browser now knows that it's audio, unlike here where it was just the link and the browser needed to figure out what to do with it. Here we tell the browser we have an audio source, right? And here we give it a name, and here we have controls, and that means this gives us the possibility to specify what kinds of kind of controls you want to give the user. Right? Here I don't really specify much. Basically everything is auto. Right? And then we can try it. Firefox demo. So going back, paste. Yeah, so here you can see now you're not just seeing a link on which you can click and then be surprised what happens, but here you actually see a player, an audio player right away, where you can where you have this control for playing back. Here you have a progress icon, and here you can also set the volume, which you couldn't do in the other one. So when I click on it, so here now it plays back, and you can actually adjust the volume. So much better than the previous one, right? Okay. Then I have another demo here, demo 2. Let's see what that is. Open the window, paste. Yeah, basically looks the same. Let's see what's different. So now I can take a look here at this file. Keep the ampersand and open it with gedit. So here you can see what's inside. So we actually see indeed is a text file, just like we saw in the slides, where we here specify our audio source, here this audio file, and some controls. Yeah, and actually if you double click on this file, then it also automatically opens the browser, because the browser knows what to do. Or better, the operating system knows what to open. So what was audio demo? Here's audio demo. So when I click on it, audio demo 2, double click, then we get this. Oh, it looks slightly different because this is now my Google Chrome. So Google Chrome has a slightly different audio player. It's also interesting. So different browsers have different players. Yeah, here you can see the codec support in different desktop browsers, but this is actually going back to 2010. So you can see it's not uniform, but it's somehow in the recent years it didn't really change that much, but I'm not sure if now every browser can do everything. So that's something you could actually check here in this link. It describes this HTML5 in more detail. And it also shows that it's still in flux, but also here the latest entry was, I think, 2014. Yeah, so now to video. Flask, I found, is quite an interesting micro web framework. Quite similar to Flash, and probably that's why you have the name. So here you can see more about Flask. And I have a little demo for live streaming of video in a website. So this is, for instance, useful if you have a webcam. And on this webcam, for instance, you have a Raspberry Pi. And this Raspberry Pi runs Python and Flask. And then you can use Python Flask to basically implement a website which shows the live video from your webcam. So going back to my window here, I need to go to the directory video streaming. So I have this directory here, and there's another directory in it, and then you can see here, make it a little bigger. that I have this main, right? More, let's type more main.py, and you can see what's in it. So this is now the Python file, the Python Flask file for running my webcam. So here you can see it, app equals Flask. Then here the camera is set up. Here it uses JPEG compression. Here it sets the video feed, basically defines what to do here. As a response, it generates the video camera. And here it starts a simple web server here in the main. If name equals main, so that means if we execute this program, then it basically starts our mini web server here at port 5000. So here host equals 0.0.0.0, which is the local host here, my laptop. And this is port 5000. This is what you need to specify in your browser as port number. So you can also do it over the internet. If you have a webcam which is accessible over the internet, then you would set your IP address here. And you could also specify a port. Or not. If you don't specify the port, then it's port 80. Yeah, so we can go into a browser. Let's take my Firefox and enter. Well, first I need to start it. I forgot to start it. So Python main.py. Ooh, no module named Flask. So I need to install it. Sudo pip install Flask. Okay. Running. So here it says, gives me a warning. It's not a production development, it's just for testing. So for production you would use Apache, for instance. And here it tells me where to listen. So I could say open link. Yes, it works. Ah, great. Hello everybody. So this is now this is the header here, and this is basically my live video feed in this web page. Okay. So here it actually also told me that what was going on, that there was an access from my browser here. So it's quite convenient and quite powerful. Right, so you can also see this example which I just showed you in this GitHub page here. So this is where I basically have it from. Yeah, and that leads me to ADPCM, which I just mentioned, adaptive differential pulse code modulation. So the principle here is that neighboring samples are usually very similar. That means we can save bits in coding if we just transmit or store the difference to the previous sample, hence the name differential. So here we have a few samples, and imagine we have a line going through, then we can just take the difference here, which is not very big. So the difference is much smaller than the samples themselves. Yeah, so if the sample is more or less a straight curve, you can roughly predict or estimate the next sample using extrapolation and transmit the difference to the pre-calculated value. The receiver performs the same prediction and adds that difference to it. The method can be extended to curves of higher order, like a quadratic curve for instance. Then only more samples from the past are needed to extrapolate these curves. This method of extrapolation is called prediction. And the application is, for instance, for lossless audio coding and for speech coders. So here's the principal structure. Here we have the encoder, here we have the decoder. The audio comes in on the left-hand side, goes into the coder, and at the same time it enters the predictor after this delay block. And this ensures that the predictor only knows the past samples, because that is what also the decoder knows for its predictor. Right. So then you take the difference here between the two, then you encode using, for instance, entropy coding. Here's decoder, has the inverse coding, entropy decoder and dequantizer. And here you have your prediction error in the decoder. The predictor here from the past reconstructed samples can also produce a predicted value at this point, and then we add the two. And then this sum becomes the next reconstructed value, which is then also fed into the predictor for the next prediction, and its output as decoded signal. Yeah, and this predictor here is usually adapted to the signal. So it's not fixed, but it's adapted to the signal for optimum performance. Yeah, the common compression factor for ADPCM is about 2. Yeah, so here a short note about stereo and multi-channel coding. So stereo means you have 2 channels, basically one for the left ear and one for the right ear. And the recording is done similarly. So you have a source, like the person speaking. You have 2 microphones, and the sound hits the 2 microphones with different amplitudes and with different delays, which means different phases. And then on the other side, it's played back accordingly, and then those 2 speakers have also different amplitudes and different delays for the source. And then the ears get those signals, and the brain then makes a direction information out of it. So if you hear it, we can tell from which direction the sound came from. Yeah, so how does the human brain determine the direction of a sound event? The answer is it uses time differences or phase differences between the 2 ears. Remember, we have this time difference. And this is done at frequencies below approximately 1 kilohertz, right? Because their 1 period is still long enough so that it's easy to compute or sense phase differences. At higher frequencies, level differences are used between the ears, so different volumes basically. And this is also called or used in panning. And it's also used in intensity stereo. Yeah, intensity stereo is widely used because it is simple for production. Here you can use volume differences or panning by volume controls, right? Or panning by volume controls, and because it is advantageous for transmission, since there are no phase differences and the amplitude differences. The differences between left and right channel become small. And this is also used in encoding. A simple method, for instance, used in MP3 is instead of left-right channels, you compute the sum, the mid-channel, and the difference, the side channels. And these are then transmitted if it is advantageous, meaning if the total bitrate is reduced. Otherwise, left-right is transmitted separately. A refinement is to apply this procedure to subbands in various frequency ranges, for instance in MPEG-2/4 AAC. Yeah, and newer compression formats are MPEG-2/4 AAC, which is for advanced audio coding. This is the successor to MP3, and the suppression rate and the compression rate is approximately a factor 1.5 to 2 greater than MP3. It's used, for instance, in Apple iTunes, in smartphones and such, and the file suffix is .mp4 or .aac. Then we have MPEG-4 lossless audio coding, which is lossless compression. which means the original samples are reconstructed exactly after decoding. This is unlike the lossy encoding of MP3 and AAC, where the reconstructed signal sounds the same but has different samples. Right? When you look at the samples themselves, they are different. Right? And this uses imperfections of the ear and psychoacoustics. And the compression factors of lossless compression depend on the signal, but usually we get again about a factor of 2. The method used is mostly predictive coding. Yeah, and finally we have MPEG-4 scalable lossless. This covers a range from lossless to perceptual coding, which is the AAC. That means you get compression ratios of approximately 2 to over 10, right? So a wide range. And an application to this lossless, scalable lossless coding is, for instance, archiving or studios with processing of the signal and several coding and decoding steps, or tandem. This is, for instance, the tandem coding problem of perceptual coding. With each encoding decoding step, the quality deteriorates. So in this way, using higher bitrate, we get a bitrate reserve before we get a problem from tandem coding. Yeah, the method used here is the so-called integer-to-integer MDCT filter bank, which allows the scalability. Right, and filter banks can also be used for processing. This is done, for instance, in Adobe Audition or in Audacity. Here's an example. So this can be used for filters, equalizers, or change this playback speed without pitch change. So often when we just increase if we directly would increase the playback speed, also the pitch would shift, right? The Mickey Mouse effect. And often you just want to speed up, say, a music piece without changing the pitch. Pitch change would be really annoying. And you can do that using this type of filter bank. So to the left you have the audio signal, for instance from 0 to 22 kilohertz. Then you decompose it into this bank of filters. So for instance you have maybe 1024 filters here. And each of those filters then covers only a tiny frequency range, which you can see here. So that means we can now also accordingly downsample because we only have a tiny frequency range. So we don't need the full sampling rate here, right? Then for reconstruction, we have the same filters here basically, and then add everything up. So if we do downsampling, we get alias components, but as long as those narrow frequency ranges don't overlap, we can fish out the correct one using those filters. So we don't have an alias problem there. But that also means we can basically change our sampling rate within wide ranges without having an aliasing problem and without shifting the frequency range that is inside here to something else. Right, so the 0 to 22 Hertz is still 0 to 22 Hertz when it comes out here. So even if we change the playback rate, so we could reduce it or increase it, the playback would be faster or slower, but the frequencies would be still within those subbands. Right, so this would be a trick to change the playback speed without changing the pitches. So very practical application. Yeah, further possibility for processing is instead of using a downsampler, we could use amplification or attenuation factors, and this way we would get easily scalable or selectable filters or equalizers. Right, so we could use this to equalize a speaker or an amplifier. Right. Okay, so that leads me to the end of this session. So thanks for your attention, and then see you next time.